Hello everyone. In the today's video lecture, we will be discussing about common emitter amplifier with voltage divider bias. Okay. So before we start with the small signal model, we have to find out what is Re. That is the equivalent diode resistance of the base to emitter junction for the transistor model particularly. Okay. So we have R1 and R2, which is an voltage divider bias from VCC, and the current IB will be entering into the base of the transistor, and output is taken at the collector terminal, and emitter is connected with the resistance Re, right? So here before we find the Re model for this, the procedure is first we have to find out the equivalent circuit after following the two procedure, that is the two rules. First is all DC supply should be shorted and all the capacitor should also be shorted, right? So once you do this, the modified circuit will be capacitors are shorted, this is RC and this is R1, this is R2, right? So we have left with only three resistance, R1, R2 and RC. Okay, and Re is neglected because when we short this capacitor, then this resistance will be neglected because the current will flow only through the low resistance path. Since we are discussing about the AC analysis, so the AC current will easily pass through the capacitor. Okay, so hence we are using this capacitor to be shorted in the AC analysis, and when we do this, the resistance Re will be neglected, hence we will not be having the resistor in our small signal model, right? So now this is the modified circuit. We have to draw the equivalent small signal model in a two-port network for this circuit, right? So first we will draw with the transistor. So this is beta Re. So input for this will be IB. So this is beta IB, and this is R0, the output resistance of the transistor, and this is collector terminal, and this is emitter terminal, which is connected to ground in this case. Okay, so now this is the small signal model for the transistor alone. So now we have to add R1, R2 and RC. So here R1 and R2 is connected from base to ground. So hence we are going to connect this R1. This is also connected to the emitter, which is connected to ground, and this is R2, which is also connected to the emitter terminal connected to ground. So R1, R2 and beta Re, and RC is connected from collector to ground. So we have this RC connected from collector to ground. So this is the complete small signal model for the voltage divider circuit with bypass capacitance. So for this, to do the AC analysis, that means to find out input impedance, output impedance and gain of the amplifier circuit. So this is my input impedance Zin corresponding to my input voltage Vin and the input current In. Okay. So here when we see the impedance between these two terminals, that means input terminal, this being plus being positive and negative of the Vin terminal, we have R1 parallel with R2 parallel with beta Re. So this itself will be the impedance, input impedance for the voltage divider bias common emitter amplifier. Okay. Fine. And here to find out the output impedance, again this is Z0 is the impedance seen with respect to these two terminals, which is V0, So when we are finding the impedance between any two terminal, all the voltages are shorted. So V in is shorted, obviously R1 and R2 and beta RE, all these three will be shorted. So the current source beta IB will be open circuit and R0 will be in large resistance. So your output impedance will be finally RC parallel with R0. So this is the output impedance. So effectively this Z0 will be approximately equal to RC because of R0 is very large. Okay, so this is the output impedance of the amplifier. Now again, to find out the gain, we will find out what is output voltage V0. V0 here is I0 into R0 or Z0, the output impedance of the amplifier. So here V0, this is the I0 current flowing with respect to V0, and this is the IC current which is flowing into the transistor. So I0 is nothing but minus IC and Z0 is nothing but RC. Okay, so this is our V0. So here V0 is equal to minus IC into RC. IC is nothing but beta IB into RC. So this is V0. Okay, so now this IB is the input current at the base transistor. Okay, if you find the input voltage or the input impedance, which is with respect to input voltage and input current I in, so this you have R1 parallel with R2 parallel with beta RE. We have obtained this. This will be approximately equal to beta RE because the R1 and R2 is very large compared to beta RE. Okay, so now IB here, so which is equal to, this is your V in or VBE with respect to IB. Okay, the current flowing to the transistor. So this can be written as VBE by beta RE or V in by beta RE, because VBE and V in are parallel. Okay, so hence substituting this IB is equal to V in by beta RE in this expression, we get V0 is equal to minus beta into IB is V in by beta RE into RC. So this will be equal to minus, taking V into the denominator, V0 by V in will be minus RC by RE. So this is the voltage gain of the amplifier circuit. Okay, and the current gain AI will be IC by IB, which is beta. This itself will be the current gain. Fine. So now if we don't have the bypass capacitance, then what will be the output, the AC analysis of the circuit? Okay, so not that we will see it now. So this is again the same voltage divider bias, RE, RC, R1, R2. This is input capacitance and output capacitance for V0 and V in, and this is your VCC. So now when you don't have this bypass capacitance, then you cannot neglect this RE. Okay, so the modified circuit will be this RE will be there. So this RC, this R1 and R2. Right, so this is the modified circuit when we start applying for the small signal model. Okay, and writing the small signal model, I will start it only for the transistor. So this is current and this is R0, beta IB, this is IB, beta RE. So this is emitter terminal. Okay, so this is collector and this is gate, sorry, this is base. Okay, so now this is the small signal model for only transistor represented in a two-port network. So now the remaining components, that is R1, R2, RE and RC. So R1 and R2 are connected from base to ground. So this is R1, this is R2, and RE is connected from emitter to ground, RE, and RC is from collector to ground. This is my RC. Okay, so now with respect to this, if you want to find the input impedance means with respect to input voltage which is seen between these two terminals and the input current IN. This is my input impedance. So whenever we find the input impedance, impedance between any two terminal, all the voltage sources are shorted and all the current source will be open, right? So when we short the output voltage, RC will be 0, R0 will be very large, and the current source will be open circuit here. So only component what you have is R1, R2, beta RE and the resistance RE. So here this Zin, what you have here is R1 parallel with R2 parallel with, I will call the impedance seen with respect to this as ZB. Okay, so this parallel with ZB it is. So Zin is basically R1 parallel with R2 parallel with ZB. Okay, so ZB is the impedance from base to reference, that is ground. Okay, so this is ZB what I have mentioned here. Now to find out the impedance between these two terminal, ZB is nothing but what is the voltage between these two terminal? It is again Vin only. Vin is from base to reference, that is the voltage, input voltage Vin, and the current is IB. Okay, the current which is entering to the branch ZB what I have reference is IB. Okay, now taking only this part ZB part for the analysis, I'll redraw the circuit. So this is Vin, this is beta RE, and this is RE, this is Vin, this is beta RE. The current flowing into the beta RE is IB, and this is RE. The current flowing into the RE resistance is IE because it is from the emitter terminal. Okay, so here by applying KVL for this, Vin is equal to, this is plus minus plus minus plus minus, Vin is equal to IB into beta RE plus IE into RE. Okay, so now IB, I will replace this in terms of IB, IE in terms of IB, IB into beta RE, IE is 1 plus beta times of IB into RE. Okay, so now this will be IB into beta, I will take common, RE plus, so this 1 plus beta I can approximate it to beta because the value of beta is large compared to 1. Okay, so RE plus capital RE. So this will be my Vin. So my Vin by IB will be beta times of RE plus capital RE. This is my effective resistance seen between the terminal, this base to ground, that is ZB. This Vin itself is nothing but ZB between the base to reference. Okay, so now this ZB will be beta times of RE plus capital RE. So my input impedance will be R1 parallel with R2 parallel with beta times of RE plus RE. Okay, so now if you see this input impedance compared to the previous, the input impedance was R1 parallel to R2 parallel to beta RE, which is approximately equal to beta RE. Okay, but here in this, what happens? The input impedance has increased. So here R1 parallel to R2 plus parallel with beta RE plus capital RE here. Okay, so the input impedance has increased. So similarly, we'll find out the output impedance. So this is Z0 with respect to my output voltage, from this being positive and this is negative, and this is my I0 for the V0. Okay, so now to find out the voltage between these two terminals, collector to ground, the procedure is all the other voltage sources should be shorted and the current should be open. When all the other voltage means the input voltage is shorted. When input voltage is shorted, R1 and R2 will be neglected. Beta Re will be again 0, because your V in is 0, so IB will be 0. So here what you have is this part of the circuit, and again the current source here will be open. So this beta IB will be open. So what you have here is R0, this Re, this parallel with RC, this R0, capital Re, RC, in this. So this is the impedance what you see from the output terminal, okay, which is equal to RC parallel with R0 plus Re. So this is RC parallel with R0 plus Re. Okay, so this is your output impedance. So effectively the output impedance, this I will write it here, Z0 is equal to RC parallel with R0 plus Re. So since R0 is very large and it is the same current, the current flowing through this here, and the Re resistance is again the same, collector current and the emitter current, which is approximately same, so it doesn't matter. So the R0 plus Re is anyhow large, so you can approximate the output impedance to be equal to Rc only. So this is my output impedance. Now to find out the gain, so I will have my output voltage expression, which is equal to I0 into Z0. So this is my I0, which is equal to the IC, which is flowing in the opposite direction. So this will be what? Minus IC into Z0 is RC, whereas IC is beta times of IB into RC. So this is my V0. So from this expression, or here itself, I can write IB as V in divided by beta times Re plus Re. So this I will substitute it here, minus beta into V in divided by beta times Re plus capital Re. So this multiplied by Rc as it is. Okay, so here this beta and this beta will cancel. I will take this V into the denominator. So V0 by V in will be equal to minus Rc by Re plus Re. So this is my voltage gain, right? So if you compare the voltage gain of the previous with bypass, so the gain is minus Rc by Re, small re, whereas here in the without bypass capacitance circuit you have gain Rc by Rc plus Re plus Re, capital Re. So this is Re plus capital Re. So in the previous also it is minus Rc by Re it is. Okay, so this is the not Ce, it is, this is Re itself. Okay, Re itself. So now this is the difference between with bypass capacitance and without bypass capacitance. What is the change? The input impedance has increased and also the gain has been reduced, whereas the current gain will remain same. Ai is equal to the output current by input current, which is equal to beta. Okay, so this itself will be the current gain, right? So this is the derivation for, or the AC analysis for the voltage divider circuit with bypass capacitance and without bypass capacitance. So for solving the problems, you can substitute the value of R1 and R2 directly, but before that you need to make sure that you have to find out the value of Re. Re will be 26 milli by IE. IE you find it using the DC analysis what we have discussed in the previous videos. Okay, Yeah, that's all for today. We'll continue it in the next class.